So guys, welcome back. So today we continue with Fourier transforms and discrete and continuous Fourier transforms. So last time we talked about Fourier transforms in general, DFT, discrete Fourier transforms. We talked about orthogonality, and we introduced Fourier matrix F and the DFT, or discrete Fourier transform matrix omega. And today we continue mainly with the Fourier transform F and the fast Fourier transform. So I'll do a quick review first. So we've mentioned the cases of classical transforms like real Fourier series, which apply to real periodic functions. We talked about complex Fourier series. We talked about Fourier integral transforms in case of complex functions, where x is between negative infinity and infinity. And the discrete case of Fourier series, which takes into consideration complex vectors f. So our focus was on the last transformation from vectors to vectors, and this is achieved, as we said, by n by n matrices. And the inverse transform uses what we call the inverse matrix. So there are some basis or basic functions to be considered. All these transforms share basis functions of the same type that Fourier used. We have a real Fourier series which use cosine and x, and sine and x. We have complex Fourier series which use complex exponentials like e to the power I n x, or n as a relative integer, 0 plus or minus 1 plus or minus 2. We have Fourier integral transforms which use complex exponentials like e to the power I k x, for k is between negative infinity and plus infinity. And we have discrete Fourier series where we have n basis vectors bk with bkj, which is e to the power 2 pi ijk divided by n, or what you can also write as e to the power 2 pi I over n all to the power k. So these are the basis function, and each function and each vector is expressed as usual as a combination of Fourier basis functions. So what is exactly a transform? As we said, it is the rule that connects f to its coefficients a, k, b, k, c, k, f of k, and these combinations are the basis functions. Combinations, let's see some. For example, real series, f of x could be written here using cosines and sines of nx and sine of nx, and we have to find these coefficients. Okay. For complex series, we can write f of x as c0 plus c1 eix plus c to minus 1 e to the power minus ix. Okay. And for Fourier integrals, we can write f of x as the integral from negative infinity to plus infinity of f hat of k e to the power ikx with respect to the integration with respect to k. And for discrete series, well, f is written as c0 b0 plus c1 b1 plus till cn minus 1 bn minus 1. In fact, it's just the product of the Fourier matrix f times the c vector. Okay? And each Fourier transform takes f in x space to its coefficients in Fourier space. So to understand what we're talking about, we are computing the coefficients, which means we are performing the analysis. We go from f to c. Okay? And if we are reconstructing f, we're going from c to f, we are doing what we call the synthesis. Okay? And there are simple abbreviations for this, FFT and IFFT. Okay? So the Fourier transform takes f in x space to its coefficients in frequency space, and the inverse transform starts with coefficients and reconstructs the original function. So orthogonality, there are some nice formulas for these basis functions, and often the bases contain eigenfactors of symmetrical points. So we can find each coefficient ck separately, in fact. So for vectors, we just take the complex dot product bkf between f and each of the orthogonal basis vectors ck. So if you can write that bkf is in details d, and here you see that we wrote f. So you can write it as the complex dot product ck by bk, which means that ck at the end of the day is just bkf divided by bk. So all inner products, in fact, bk vi are 0 in this equation, except the one which have the intersection bk. And those denominators are either equal to pi, 2 pi, n, and are very easy to perform, to obtain. So the series we can talk about here, we have the integral of cosine nx to the power 2, which gives always pi, the integral of sine nx squared, which always gives pi, or the integral of 1 squared, which always gives 2 pi on the period 0 to pi. For the complex series, we have the integral of e I k x times e to the power minus ix, which gives also 2 pi. And for discrete series, where we have here the complex dot product, bkt ibk, which always gives n. So if we normalize the basis vectors to magnitude of bk equals 1, the matrices are orthogonal. And the Fourier integral case is the subtle one, and we stop after writing down the equation. So it has an infinite integral form, which comes from the Fourier transform, okay? When we talked about last time. Okay. So finally, last time we reached that slide, I think, or the next, where we said that you have two main matrices, the Fourier matrix, which in fact writes as 1, 1, 1, 1, 1 in the first column. Then you can see the next column, you have 1 I squared, A3. So that is an easy pattern to recognize. And its conjugate is what we call the omega, or the DFT matrix, the discrete Fourier matrix. And it writes, as you see, it's just the conjugate of f. Okay? So the matrices Fn and omega n are always n by n. They're both symmetric but complex, and they do have the same columns, but the order of the columns is different. Fn contains powers of e to the power 2 pi I over n, and omega n contains powers of the complex conjugate. Here, there was a small mistake here. It's W here. W here is the Latin letter, and its conjugate is what we call the small omega letter in Greek. Okay? So here there is a small typo. It should have been omega. Okay? Should have been removed. So the conjugate is, as you know, from complex analysis. You can write it as e to the power minus 2 pi I over n. So in fact, the two matrices are complex conjugates. And you can write the conjugate of Fn, which is omega n. And for example, here are the two examples of F4 and omega. Okay? So now some remarks. Omega times f produces the discrete Fourier coefficients, C, and f times c brings back the vector for f, or nf, because f times omega is nf. So one step, as we called it, is the analysis, and the backward step using the omega is the synthesis. So if you multiply Fn times omega n, you discover a fundamental identity for discrete Fourier transforms, which is that Fn omega n is equal to Ni. So in other words, the inverse of the Fourier matrix, Fn, is easily obtained as 1 over n omega n, or 1 over n, since omega n is Fn conjugate, you can easily obtain. The n numbers are equally spaced around the unit circle, and we've shown a drawing last time on how to place them. And at the end of the day, these n numbers, they solve this complex equation, z to the power n equal to 1. And more than this, their sum is always equal to 0. And the proof is quite easy to obtain. So the discrete Fourier transform. Now let's see some more practical things. So you start with n-dimensional vector f, and the discrete Fourier transform expresses f as a combination of the coefficients c's and b's of the basis component b0 to bn minus 1 by the coefficient c0 to cn minus 1 of the Fourier basis vectors. So these basis vectors are the columns b in the Fourier matrix. So this is your vector f initially. Okay, and you want to write it like this, as the product of the basis vectors, the b vectors, by the coefficients you are looking for. So therefore, one can write f as fn times c. So c, in fact, if you want to retrieve it, is fn inverse times f, and therefore c is 1 over n times omega n times f. So this is how to find it. Okay, so this is when you do this, what you get is the analysis step. So this is the forward transform C, which applies FFT to F and multiplies F by the DFT matrix omega and divides by F. That is the analysis step to separate F. In fact, what happened to F when you multiply by 1 over n omega n, you separated F into n orthogonal pieces because the B's here, the B components are orthogonal, okay? With each one is coefficient. So in fact, the DFT finds the coefficients in a finite Fourier series. So your vector is now written in using a finite Fourier series. Okay, you see how beautiful it is. Now the backward step, the synthesis step, is the inverse transform. Okay, where you are using the IFFT. Okay, the inverse Fourier transform, and you want to retrieve F from C. So you multiply C by what? By your Fourier matrix F. So it starts with the coefficient C, if you have them, and it carries out a matrix vector multiplication FC to recover F. So thus, when you perform them twice, you get the identity. When you apply FFT, then R inverse of IFFT, you get like F. So in the following examples, we'll throw the light on the two vectors F and C. So for example, this is the first example. The transform of F1000 here is the following coefficient vector, 1 over n, 1, 1, 1. And you see how it's spread like frequencies. In fact, what happened to F is that just one spike. There is only one entry which is non-zero, which is the first entry, which is a discrete delta function. And as you can see, it is concentrated at one point, and its transform, as you see, spreads out all over frequencies. Okay? It spreads out the one all over frequencies. So if you multiply omega by F, you are taking out the zeroth column of omega. So as you can see here, for n equals 4, for example, how do I obtain C? So this is F as you see it. Okay, I have only the first entry, which is 0. I'm multiplying by the omega matrix here. Okay, and divided by n. So if I do the multiplication, I'll show in detail in the next slide. So if I do the multiplication, I get from 1000, which is F here, I'll get the C vector, which is 1 over 4, 1, 1, 1, 1. Okay, and if you want to go backwards, you're multiplying, as you see here, F by C. So you see now immediately these are the columns of F. Okay, as we've seen without the product multiplication. And you see how when I multiply F by C, I get exactly 1000. Okay, got it, guys? So this transform C of a delta vector F is like the continuous transform of a delta function. So the delta function concentrates everything at x0, and its Fourier transform spreads out flat the delta function using finally finding out at the end 1 over 2 pi for every frequency. Okay, so it's like a discrete case for the delta function. Okay, so let's see with the next example. So one can see that 2 pi here plays the role of transforms transforms like n in the discrete one. So for example, if your F here is 1, 1, 1, 1, 1, its transform is the following. It gives you concentration C, which is n0000. Okay? If you do a shift compared to the previous case, so the one is no longer in the first position, but in second position, you produce what we call a modulation. So if you multiply omega again by 0, 1, 1, 1, you get the following C, as you see. Okay? And if you want to go backwards, you multiply this C you obtained by F, you get that F, as you see. So you just multiply here by 1. Okay? So, which means that a shift in X space is a multiplication of the coefficients in K space. Now, Noah, go ahead, please.
The F111, how it become to the F0100 after the shift? I didn't get it.
So when you do the multiplication here, okay, let's say I do the matrix multiplication F, which contains all these columns, by this this vector C. Okay, are you with me?
Doctor, I mean the second point, F equal 111.
This case. This is just another example. This, if your initial F is spreading down 1 at every position, then when you multiply by omega, you get n000. Okay? Why? Because omega, in fact, you have omega, which is 1, 1, 1, 1, 1, 1, 1. And here I have minus I squared, minus I cubed. Okay? So if you multiply by the F, you're collecting the n's in the first position because you have 1. Are you with me, Nawab?
Yes.
Okay? The first position you get n because you're just summing n times 1, right? But when you move to the second row, you will always have that sum of 1 plus minus I plus minus I squared plus minus I cubed. You get my point? So it's always going to be ending up to be 0, as we've seen it in the property. You get my point?
Yes.
All these elements are obtained by the sum of 1, for example, plus minus I plus minus I cubed, something like this. So when you get to n, you get the 0. That's the property. So all these these elements are going to be equal to 0. Okay? So if you go backwards, multiply by F, you obtain the F again. Obtain by capital F, you obtain your vector. Okay? You can, it's easy, it's amusing, a little bit entertaining if you want to try to do it. The examples are pretty straightforward. Okay? Now, but the point is that now we'll talk about fast Fourier transform. So now you see that multiplication could be taken a long time, and in fact it would take n to the power 2 operation. This is not a script, not a subscript. So we want to multiply now F times C as quickly as possible. So normally a matrix times a vector takes n to the power 2 separate multiplication, because the matrix has n to the power 2 entries. Okay? But we want to do it so, but when n increases, what happens? The number of operations becomes quite huge. So we want to use some special patterns based on these coefficients we have, the w's, for their entries. Omega and f can be factored in a way that produces many zeros. And this is what we call the fast Fourier transform. The key idea is to connect Fn with the half-size Fourier matrix, let's say Fn over 2. So let's, for example, assume that n is a power of 2. For example, if n is 2 to the power 10, which is 1024, in fact, we can show that F1024 connects to F512. When n is 4, the key is the relation between F4 and 2 copies of F2, the Fourier matrix of size 2. So let's see this case. So in fact, we need 2 sparse and simple matrices to complete the FFT factorization in that case. So F4, which has this shape, 1, 1, 1, 1 in the first row. Then you have 1, I squared, I cubed, 1, I squared, I4, I6, 1, I cubed, I6, I9. You can write it using this following factorization. Let's focus on the middle. What we have here is F2, in fact. This is F2. See it? Okay. Now, I'll detail what we are bringing in front on the right and on the left. The last matrix is what we call a permutation matrix. In fact, it puts even C's, even coefficients, C0 and C2 ahead. C0 and C2 ahead. Then the odd C's in the last rows, C3 and C1 and C3. So this is for the right matrix or the last matrix. The middle matrix performs half-size transforms, F2 and F2, as you've seen it between. You have F2 and F2. And the even C's and odd separately. So when you're going to multiply the F2, you're going to multiply by the even and the odds separately. The matrix at the left now combines the two half-size outputs in a way that produces the correct full-size output, which we can call y equals to F4C. Okay? So now the same idea could apply also to the much larger case when n is 1024 and n could be supposed to be equal to 1/2 of n, 512. The number w, which is e to the power 2 pi I over n, which is 124. The angle you see is very small on the unit circle. And in fact, the Fourier matrix F 1024 is full of powers of w in that case. So what has been shown by Corey and 2K is that the first stage of the FFT can be obtained with a great factorization. So you can write the Fourier matrix 1024 using the identity matrix of size 512 and the D matrix with size 512 and the Fourier matrix of 512. What is it? The identity 512 is the identity matrix of the corresponding size. D512 is the diagonal matrix with all entries from 1W till W511, as we presented before. We gave the formulation of the W corresponding. And the permutation matrix at the end, in fact, separates incoming vector C into the even part first and the odd parts and put them in the permutation matrix. Okay? So the last two steps here, I prefer to leave them to the next time to see how it works. So this is a one step of the Fourier transform, and we need to apply. We use MATLAB to do this. Okay. So this is to complete 3.4.1 on the discrete and normal case Fourier transforms, and we can use them to transform a vector of a vector to coefficients and coefficients to vector.